Assalamu alaikum, dear students. Welcome you in a new lecture series, that is in lecture 3, okay, relating to structure analysis program. Clear? And in this lecture 3, inshallah, we will discuss an overhang beam, okay, with a UDL and having a moment, okay, a flight moment. Okay, so this is, it is a different beam. Clear? It contains a UDL at some certain span, and it has a moment. So here you can learn a little bit different, that how we can assign this kind of UDL and how we can assign a moment to a, a beam or a member. Clear? So you must know about this thing, that about the movement, that how movement is assigned to a structure, okay, and how movement is basically acts, and how the movements is basically applied to a structure in clockwise and anti-clockwise direction. So let's see. First of all, you need to confirm the units, that is found feet. So you need to select your units right from here, okay, that is found feet. Clear? And then you need to insert your new option, okay. You have overhang, so overhang has two spans, and you have a span length, different span length, okay. You have AB span, and as well you have BE, but in shape basically you have BC span. Clear? So we will just only insert the AB span, that is 2 feet, and then we will edit the grid spacing, and then we will adjust that 4 plus 1, and 1 gives you 6 feet. Clear? So let's see. We will edit this grid spacing. Clear? And here we will check our unit should be in found feet. Clear? And your spacing should be selected, and there you can insert only, you have to insert for AB span, that is 2 feet, and for BC span, that is 6 feet. Clear? Straight feet. And the rest of data will be as uh, as well as okay. You don't need to make changes. Okay and okay. Clear? You need to delete this one, okay, and make sure that you will be in XZ plane. Clear? You need to remove this join. For that purpose, select join, assign menu, join and restrain, and okay. Now you need to convert this ruler, because if you cannot assign two rulers to a statically determinate, because although it is determinate, but it is statically unstable. It is an unstable structure. So you for a simply supported structure, it should be necessary and mandatory, you can say, that there should be one hinge and one ruler. Okay, so we will assign this this one will be a hinge, and this one will be a ruler. Clear? This one will be a ruler. Clear? Now this is our required beam. Clear? Now we need to assign the loads. Okay, so we can assign the loads in two ways. Okay, the first way, I will assign the load first of all to this span and then to this span. Clear? And then in the next step, I will assign I will mention you the second method, that how you will assign the load in one step to the whole beam. Clear? So let's see. This is step 1. Clear? That how you will assign frame loads, distribute it, and the dead load multiplier should be equals to 0. Clear? Modify. Okay, and then you should make sure force unit will be add to existing loads global. Okay, because this is acting in the coordinates are global. And gravity means it is acting downward, load is applied downward. And here you select absolute, but you don't need this spacing. Okay, you just need to insert 100 pound per feet. Okay, so the load is assigned to the overhang portion. Now we need to assign the load from B to C, that is 4 feet. Clear? So B will be 0 and C will be 4 feet. Clear? So let's see. Now this point is 0 and 4 will be our ending point. Clear? So assign frame load, distribute it, make sure that unit is same. This should be check gravity, and now we will use spacing. This should be 0. Clear? This should be 0. Now at 0 feet we have 100 feet. Clear? At 0 speed, at 0 distance we have 100 feet. Clear? And at 4 feet, at 4 feet we have 100 feet. And then at 4 feet, again at 4 feet we have 0, 0. Okay, so let's see. This is the way. Clear? This is step number 1. Okay, or you can say this is method number 1, that how we will assign loading in a two-step way. Okay, such type of loading. Okay, when it present over a two portion or two span. I will show you the next method. Let's say Control Z, Control Z. Okay, you select this, you select this. Okay, now coming to assign menu, frame loads, and you need to select distribute it. Okay, here dead, pound feet, forces, global, gravity, add to existing loads, and here you will use the spacing. Okay, so it's 0. Okay, at distance 0 you have 100 feet. Okay, then at a distance 2 feet you have, at distance 2 feet you have 100 feet. Okay, and then at a distance 4 feet, at a distance, you can say at a distance 4 feet you have 100 feet. Okay, or you can say that again yes, at a distance 4 feet you have 100 feet. Clear? And then you will say that at a distance 4 feet you have 0 value. Clear? Because after 4 feet you have 0 loading. Clear? So let's see. This is the way. This is another way of assigning the same type of loading with a different way, with a different method. Clear? I think now you will understand the two methods, that how we will assigning loads. Clear? In a different way. Now we will assigning movements. Okay, and the movements is a little bit a different way. Okay, movement is a little bit tricky, you can say. You must need to understand now axis. Clear? Because if you don't understand the axis, this will be a little bit tricky for you. Okay, so you have global axis. Global axis or global coordinates means that the axis which remain constant for, you can say, for this whole beam, and it doesn't change. Okay, so those global axes you see here, that you have z axis over there. Okay, and your x axis over there. Clear? Because we are basically in exit plane. Clear? So exit plane means that your z axis will be this one, and your x plane will be this one. Clear? Now where is your y axis? Your y axis lying, which is passing through the screen of your computer, which is passing through the screen of your software. Okay, so that is inside your screen. That is your y axis. Clear? That is your y axis. Now basically this Z is representing the width of my screen, and the x-axis is basically representing the x-axis, the length of my screen, and the y-axis is basically representing the thickness of my screen. So in beam case, if you convert it into 3D, if you convert it into 3D, like this, clear. So if it is 3D, okay, if it is 3D, so here you can easily understand that, from here you can easily understand this axis is basically representing y, this length of beam is basically representing x, and the height or the depth of the beam is basically representing the z-axis. Clear? Now basically this is the most important, because sometime in SAP you can see 1 1 2 2 3 3 axis, because in lecture 1 and 2 you see that we calculate moment about 2 2 or about 3 3. We calculate moment about 3 3, and we calculate shear about 2 2. So in lecture 1 I will say that I will explain this topic in later lectures. So here I am defining, okay, basically x-axis is representing 1. 1 means it representing x-axis. 2 is basically representing z-axis. Whenever you are seeing 2 2, this means it representing z-axis or z-axis, and whenever you are see 3 3, so 3 3 means this means that it is representing y-axis. In SAP structure analysis program, basically 1 representing x, 2 representing z, and y representing 3. This may be changed, okay, sometime, but basically structure analysis program works on this axis, okay, in which x-axis are representing 1, y 3, and z 2. So here you can see the moment is basically applied, in this manner, okay. The moment, you can see this is the beam, and the moment is applied in this way, clear, that is 1200 pound feet, and the direction is in this way. So you need to understand that the direction of the movement is clockwise, so the value which we will insert in the window with a positive sign, okay. One thing you must remember, if this movement is applied in an anti-clockwise direction, you will insert the value with a negative sign, clear. But the question is that you need to understand that the moment is applied about what axis, because whenever we applied a moment, it must be applied about an axis. Now here you clearly understand, as the moment is applied in this direction, so if you compare these axes with this moment, okay, with this moment, so if I draw my moment axis, okay, like this is my y axis, this is my x axis, and this is my basically z axis, clear. So from this figure you can easily understand that the movement is applied about what axis, about y axis, not about x axis, not about z axis. If it is applied about x axis, so the representation on the xz plane will not be possible, or it will be representing somewhat like in this way. There will be x and there will be movement. So here it is clear that from this figure you can easily understand that the movement is now applied about y-axis, and you can easily apply the right hand rule, okay, the right hand rule. So the thumb, basically the thumb finger is representing the direction of the movement, while the curl fingers, that representing the value of the movement. So from this, whenever we are at the last, basically in lecture 1 and lecture 2 and this lecture as well, we will calculate shear about 2 2 and moment about 3 3. Why we are calculating moment about 2 2 and about 3 3 and shear about 2 2? This means basically you can see the beam is supported at this edge and the beam is supported at this edge. Clear? So as from this axis you will easily understand that once the beam is bending, okay, for example, if I draw a neat sketch, okay, let's say this is my joint and this is my another support. So for example, if my beam is bent in this way, if my beam is bent in this way, so here you can see that the rotation of the beam from its initial axis like this way. So this is, this is your movement, this is your rotation, and now you need to compare this rotation with your axis. So if I compare this rotation with my axis, so this is my z-axis and this is my x-axis, means this is my 1 1. Clear? This is my 1 1. This is my z-axis. This means that this is 2 2. Okay, this is 2 2. And this is my y-axis. This means this is my 3 3. So here you can see that this rotation is about what axis? This rotation is obviously about 3 3. So therefore we will calculate moment about 3 3. Not about z 2 2, not about 1 1. In later stages, when we are analyzing and when we are assigning moments about in space frames, we will determine the moments about this 2 2, this 1 1 as well. We will see it, okay, in 3D space and 3D frames, okay. So but at this stage, whenever we are analyzing or designing 2D frames, 2D beams, 2D trusses, okay, so in all cases of 2D beam structures, okay, you will calculate shear about 2 2 and moment about 3 3. This should be keep in mind. Clear? You must always remember that shear will be about 2 2 and moment about 3 3. Clear? So this is a very important question, why we are using 2 2 and why we are using 3 3. So I think it will be very large data about 2 2. In later lecture, inshallah, in coming lecture, you will see I will also explain more information about these axes. So here we have a movement which is 1200 pound-feet at a distance 0 to 5 feet. Okay, the movement is applied in a clockwise direction, okay, at a distance of 5 feet. So let's see how we assign it. So the movement is applied to this plane, so I select this plane. Clear? Coming to assign menu, frame loads, and you can select point or you can select distributed. Okay, let's say distributed. Here you need to select option movement. Unit should be checked, this should be checked, okay, and here you need to change the direction. So as I mentioned that the movement is applied about y-axis, so y-axis should be selected, and the movement is applied in a clockwise direction, so therefore you need to make it 0. Clear? You need to make it 0. Clear? You need to make it 0. Clear? So we have a movement which is applied at a distance of 5 feet and the value of the moment is 1200 pound-feet. Clear? So let's say okay. Now the moment which is assigned to this beam, you cannot see them in a xz plane, even in xy plane, even in yz plane. Okay, if you want to see the movement which is applied to the structure, you need to select the 3D view. So in 3D view, and you need to rotate the structure, so you can see the movement is not assigned to the structure. Okay, the movement is not assigned to the structure. If you are conforming, so comes to show loading and there. Okay, so the movement is not assigned. Okay, so let's see again, try it. Okay, so select the structure, assign frame load, and let's say point. Okay, moment, and you need to select y-axis. Okay, and select absolute distance, and at a distance 5 feet. Okay, and you have 1200. Okay, and select this option, moment found feet. Okay, now I think so the moment is assigned here. Why the first step, basically the moment is not assigned because we select the distributed load, and moment is not a distributed load. Moment is, you can say it is just like a point load. Clear? It's just like a point load, so therefore the moment is not assigned in first step. Clear? That is the reason. Now you can see the moment is not applied in the way as shown here. This is not in this way. The moment is not applied in this way. Okay, the moment is applied in shape. Basically it is shown like in this way. Clear? So you must know that whenever the moment is applied to a structure in this way, that is, like in our present case, this is 1200, so this means this is positive movement, means this is clockwise movement. And if it is in this direction, so this means the movement is in anti-clockwise direction. Clear? And they must be applied with a negative sign. Okay, they must be applied with a negative sign. So here we have positive movement, that is x-axis, so therefore it is a with a positive sign. Okay, in this direction. So coming back to x direction and just checking the load, whether all the loads are assigned or not. So here you can see this option now work. Okay, so at the first attempt, this option is disabled, it don't work. Now it works. This means the load is assigned. Okay, and you can if you are interested to see your UDL, so the UDL is also applied. Okay, now we are in analysis position, so let's see. In analysis, model do not run. Okay, and run now. We need to save the model. Clear? Movement overhang. Okay, so clear. This is the structure. Clear? Now first of all we want to check the joints reactions, 300 and 300. I think so it is okay. 300 this one and 300 this one. Clear? Now we will check the shear diagram, that is minus 200, 100 and minus 300. So let's see. You need to select the same option, frames. Okay, and now you need to check shear. As I already mentioned, you need to check shear 2. Clear? Values. Okay, so this is the diagram. Okay, you can make clear these values by just selecting the option of maximum and minimum graphics, as I explained in lecture 1. From there, I think so, here maximum and minimum. Okay, I just using the window option. Clear? So this is minus 100, 200. Clear? And this is 300. So I think so the diagram of shear is okay, the values are okay. Now let's see what are the values of moment. So moment about 3 3, I explain you why we 3 3. Okay, so I think so it is also clear. Now 900, 300 and 200, and I think so you can see 900, 200 and 300. Clear? So this is the way that if you want to determine the values at these points, you can follow the same procedure as I mentioned you in lecture 1 and lecture 2. Clear? So basically this is the procedure that how we will analyze the structure, okay, the overhang beam with a UDL and a moment. And I think you will understand that why we are calculating V22 and V33, M33. Clear? And you must know about the axes, their representations. Okay, so if you become the master of the representation of axes, I think it will help you a lot, okay, in your coming lecture, because at this moment this is a little bit simple. Okay, you have just only one element when we are analyzing frame structures which have a number of members, so this will become more tricky and more complicated. So I think this is enough. See you in next lecture with an overhang with some sort of different loading. Thank you.